So we have Anirban as our next speaker, and he will be talking about selecting the safest design in rare events.
Hi everyone. So this presentation is based on a recent work with Professor Sandeep, and I got accepted to the Winter Simulation Conference 24. So here's how we'll proceed with the presentation. We'll introduce a special kind of simulation problem where, I mean, how do you put it? So there are systems that rarely fail, but these failures can have catastrophic consequences. So that is the area we'll be dealing in. We'll model these kind of catastrophic rare failures as a best time identification bandit problem. And then we'll look at the lower bound for sample complexity in best time problems, which Agniv has already explained. So maybe I will just cut it short there. Then we'll introduce the rare events framework into the into our best time identification problem. We'll see that it leads to some interesting approximations. And once we solve the lower bound problem using those approximations, it gives us some interesting structural insights. That is one part of it. And if there is time, we'll also talk about how the track and stop algorithm, as Agnew said, can be, we can just streamline the process of the track and stop paradigm and get an asymptotically optimal algorithm. Track and stop is asymptotically optimal as it is, but we just streamline the sample collection. However, there is also a small caveat. In case of rare events, the lower bound, as we know it now, may not be a tight one, and we'll see why. So this is broadly what we'll cover, and in the end, if there is time again, we might talk about some more generalizations to the probabilities of failures. We'll get to that. Okay. So, like we were saying that let us have K highly reliable systems that rarely fail. Probability of failure is very low, but if they fail, we are in for big trouble. Like you can see a nuclear reactor, you can see a power plant. These things hardly fail, but again, if they do, we are in trouble. So what happens is we cannot actually run these systems for thousands or millions of times to see when they fail and then get good estimates. So we need simulation models for these systems in place, and we'll generate IID samples from these simulations, and the failures will mimic the failure probability of whatever system we are simulating. So, selecting the most reliable system from a given set of systems has been studied in the simulation community as well. Like they call it the ranking and selection problem. However, ranking and selection problems typically deal with Gaussian distributions only. In this case, we will not be dealing with Gaussian distributions. We will be dealing with Bernoulli distributions because we are concerned only with failure or non-failure. Okay. So, which is why we bring in the best arm problem, because like Agni was saying, that a single parameter exponential has been studied in much detail over there. So we'll use the best arm identification framework to model the current scenario. We have already, I already said that if we use some certain approximations for rare events, we get interesting structural insights into the optimal weight allocation. We'll be looking at that, and the delta characteristic. So best term identification again, it's basically sequential decision making. There will be K probability distributions. We can sample from these distributions, and what do we want to do by sampling from these distributions? Given a confidence parameter delta, we want to declare the optimal arm with probability at least 1 minus delta. So the algorithm stops at a finite stopping time and says that such and such arm is the best. The fact, the probability that this arm is actually the best is at least 1 minus delta. The distributions we are labeling as eta 1 through eta k. These belong to some family that will be known to us, and we can call that family script key. All right. Now, for any problem instance that we take from P, and for any delta greater than B, if an algorithm can declare the optimal arm with probability at least 1 minus delta, then we call that algorithm delta correct. And what we want to do is minimize the expected number of samples for delta correct algorithms. So, like again, for single parameter exponential family, Bernoulli is no exception. The distributions can be characterized by the mean. So when we talk about KL divergences, we'll often just write KL divergence between the means. This may be seen as a slight of notation, but I mean, it's just easier if written like that. So we'll take that. And for Bernoulli distributions particularly, you can see this form of KL divergence. Perfect. So let's get to the road model. Like we were saying that we will be treating any distributions and means, the notation we will keep interchanging. So ith system, suppose it fails with probability eta I, and the first system is we have a unique safest system. Again, so from here onwards, we'll be interchanging between best arm and safest system for obvious reasons. Okay, and as opposed to the system one being the safest, we have alternate hypotheses, which will represent by kappa. So, kappa belongs to the alternate conclusion set where the first system is not the safest. And again, from the data processing inequality, we get that. Again, I mean, I will not get into the details of this one once more, but we get this kind of a KL divergence times expected number of samples given to the ith arm. The weighted sum of this is looks like a log 1 by delta. Now, if we want to minimize the overall sample complexity, then we get this kind of a max-min problem. Note that we are getting this kind of an expression because let's get here now. See, KL divergence between eta and kappa. So eta belongs to our eta belongs to the conclusion set where arm 1 has the best mean. Kappa belongs to the conclusion set where arm 1 does not have the best mean. So when are we likelier? I mean, when do we get the most confused? When in both eta and kappa, barring the first arm and some ith arm, every other arm has the same. So, and between the first arm and the ith arm maybe has more mean than the first one. Right. So what happens is this d eta I kappa I reduces to 0 for all but first and ith arm. And that is how we land into this kind of an expression. So you can see that we are saying eta I prime is bigger than eta 1 prime. That's how we landed into this expression. And again, because we are minimizing, so the most confusion is created when, I mean, for every ith arm, we take the minimum of these quantities, these weighted sums, and we map instead of ni, we are considering the proportion of samples allocated to each arm. So we substitute them by W1 and W1. W1 is basically like N1 by summation N. That's it. And now we have that W1 till Wk must lie in the probability simplex. And that gives rise to this kind of a gigantic max-min expression. Okay. For Bernoulli bandits, in fact, for any single parameter exponential bandits, Agnew has already shown that we have this kind of a weighted expression. So, pardon the CIs here. Actually, we all in our analysis we also assume that the different systems that we are simulating different systems can have different simulation costs. In that case, the CI and C1 represent the simulation cost for first system and IL system. That will not be largely a part of our discussion today because, I mean, not having the computation cost kind of drives home the insights better. So I've just kept it for the end. Okay. Uh, Now, why is it important to understand this Maxwell problem better? Because uh, as Agni has already shown, we have this well-known family of asymptotically delta correct, asymptotically optimal delta correct algorithms that we call track and stop. So for track and stop, we need a really good understanding of this quantity because again, it's also expensive to compute. So wherever we can cut the cost of computing it, we want to do it. All right. So let us now incorporate rare events into this. And then we'll see what approximations we can do, right? So remember that ith system was failing with probability eta I. Now let us give eta I a more concrete form. So eta I is some order one constant times a small number raised to a positive number. So P1 times gamma raised to alpha 1. Gamma can be seen as a rarity parameter, and alpha is like alpha 1 through alpha uh, are different orders of rarity. Like if suppose alpha 1 is, let us say gamma is something like a 0.1 and alpha 1 is 2, alpha 2 is 1, then we are just saying that the first arm fails about once in every 100 times, second arm maybe fails once in about every 10 times. Right. So that is the flavor of the rarity framework right now, but this will generalize. Okay, now what we'll do is we'll let this rarity parameter gamma tend to 0. And as can be expected, like if you look at the KL divergence expression for Bernoulli, uh, if we have some gamma going to 0 over here, it should lead to nice approximations, right? We'll be seeing that. Okay. So as gamma goes to 0, we'll develop structural insights. One key result that we are going to see is lower bound on expected sample complexity is order gamma raised to minus alpha 2, not alpha 1. Right? It's minus alpha 2. So what is that basically saying? If there are three systems, suppose one system fails once every 100 times, one fails once every 1,000 times, one fails once every million times. So basically, if we consider like a gamma is again 0.1, then we have alpha 1 is 6, alpha 2 is 3, and alpha 3 is 2. Accordingly, we'll only need a few thousand samples to say that, okay, this guy is the best. And I mean, there is a commonsensical explanation to this because, I mean, by the time we have seen a few thousand samples in all the arms, what has happened is this arm has failed several times, or this system has failed several times. This system has also failed a few times, but this guy has not yet failed. So, I mean, this guy not yet failing, I mean, while going by the track and stop paradigm, we basically keep tracking the generalized log likelihood until a particular threshold, the threshold of log 1 by delta is reached. Okay. So, we can get into the structural insights. All right. So, in order to get into the structure of the optimal weights with clarity, we'll have to break down our problem instances into three cases. In the first case, we have alpha 1 greater than alpha 2 greater than alpha 2. So basically, if the rarest system fails once every million times, then the second rarest system does not fail once every half million times or something. Or maybe I should say if the rarest system fails once every 5 million times, the second rarest system will not fail once every million times or so. It will be in order of thousands or something like that. So alpha 1 will strictly be greater than alpha 2, and alpha 2 will also be strictly greater than alpha 3 in the same fashion. This kind of instances we will denote by U1. In case of U2, you'll see that alpha 1 strictly greater than alpha 2, but alpha 2 equal to alpha 3 till something. So you can think of it as one system failing once every million times. The second system maybe fails once every 300,000 times. Third system fails once every 200,000 times. So the rarity in that sense is decreasing, but the order of rarity is about this. In that case, we have a different structure to the optimal weights. And lastly, the rarest system, it is uniquely rarest, all right, but the order, I mean, there are other systems with the same order of rarity. So alpha 1 is equal to alpha. So again, in this case, we'll have to examine separately. What happens when we do this? Just recall the maximum problem that we are trying to solve. We want WJ stars that solve this problem, and we want to know what they look like. The first interesting insight is in case of U1, okay, when alpha 2 is strictly greater, less than alpha 1 and strictly greater than alpha 3. In that case, the best arm gets 1 minus 1 by E proportion of the total samples allocated as gamma goes to 0. The second best arm gets 1 by E proportion. And as you can guess, the optimal weight of every other arm goes to 0. Right? That brings us to, and this, for every alpha j strictly less than alpha 2, the Wj star goes to 0. It just so happens that this is true for each of our partition sets. So where we are different is when Wj star does not go to 0. Turns out that when Wj star does not go to 0, for every j such that alpha j is alpha 2, we do not have these nice closed form expressions, but we can reduce the first order conditions of the.
So when you say that the competition will go to 0, even when gamma is also going to 0.
When gamma goes to 0, yes. So for weights with non-zero limits as gamma goes to 0, in case of U2 and N, we have slightly simplified systems of equations that will give us the answer. So the formal result kind of looks like this. I'll just let this stay for a minute and so this is the U2 result and this is the N result. So not only are we saying that Wj star goes to 0, we are giving the rate at which it goes to 0. Right. Now, this will actually be telling us why for rare events this lower bound may not be tight. Okay. So okay, I'm moving on to the next step. Okay. So, like we said, for rare events, we have these approximations. You can see like instead of actually calculating logarithmic expressions and doing all the algebra, when we have these kind of approximations, naturally, if we substitute these KL divergence into the lower bound problem, we get much cleaner insights. So that's how we were actually able to land into those equations or the closed forms for theorem 1 that we saw. So how we go about it is of course, we come up with these approximations. These are simple things. Mean value theorem will give you this. Okay. Now, for alpha I strictly less than alpha 1, we have one pair of approximations. And for alpha I equal to alpha 1, we have another pair of approximations, which I have not shown here because they are just today. But what I want to say is, if you see, this approximation is of the order gamma alpha I, which is going to be much lesser than gamma alpha 1. So we are not very far off from where we should be. Again, if you see when alpha is equal to alpha 1, the KL divergence will be of the order gamma alpha 1, which is significantly smaller than the error that we are having. So we are well placed to move forward. These approximations when placed will directly give us this form of the lower bound. Okay. Right. Then, like I said, once you have these approximate forms, you just substitute them into the first order conditions and you get the result. That is simple. And also, we need to show that these limits are actually close to Wj star. For this, we take a slightly roundabout route, as in, because we are solving an approximate problem. There is a lot of approximations going on in the sense that, first you have approximate KL divergences, then an approximate problem. And then that problem actually gives you approximate solutions. So what we actually show is Wj hat is close to the approximate solution, and that approximate solution is close to the W star. That's how we go about it. I have hidden the details for like scarcity of time. That's it. All right. So, like we saw for every j such that W star goes to 0, it has this kind of an expression, right? So, what happens is we have already seen that we have a lower bound on sample complexity of order gamma raised to minus alpha 2. So, if you kind of see for each r gamma minus alpha 2 times gamma alpha 2 minus alpha j divided by log gamma raised to minus 1. Okay. Now, what is it telling us? That if you give gamma raised to minus alpha 2 samples, gamma raised to minus alpha j divided by some number bigger than 1 will be the number of samples that the jth arm will see, right? But if the jth arm fails once every gamma raised to minus alpha j times, and we are not even seeing gamma minus alpha j samples, then how can we say that, how can we kind of say that it is not the best? There is a bit of a paradox here, right? So now, mm, because we have to see at least order gamma minus alpha j samples to be able to see anything about the jth arm. So what we are saying is that the lower, and because we are getting this kind of an expression due to the lower bound problem. So the lower bound that we are being given is probably not as tight as it should. So there is scope for further research into this. All right. And optimal algorithm is basically track and stuff. So now, in general, for the exploration phase, root and many samples are sufficient. But in this case, it might not be true, right? Because you have one arm that fails once every 100,000 times, something that fails at once every 100 times. So we cannot do a uniform allocation. That part needs to be corrected. One thing, and apart from that, again, the sampling rule, it is governed by the prescriptive proportions as given by the solution to the lower bound problem. That's how we sample, and we stop again when generalized log likelihood exceeds a well chosen threshold. Beta tau delta basically looks like log 1 by delta. It can have variations, like there is something suggested in Kaufman 2016, there is something in Kaufman 2021. And so another thing is this sampling, this form of sampling and this form of stopping together, what we will call them is the plug and play approach. Okay, and I have just added a comment on the GLLR, which Agni was rendered unnecessary now. Okay, so what do we do now is we start with giving 10 samples to each other. And suppose we see nothing in any arm, then we get it up to 100. Again, sample everything. If we keep raising this by a factor of 10, at some point of time, we'll see we'll see failures in some systems. That's where we start computing the GLLRs. Now, we already have a well-chosen constant threshold. Whenever a GLLR exceeds the threshold, we don't sample that arm, right? We also take another step. If we see sufficiently many failures in any system, let's say, for our algorithm, we use 20 failures. There is nothing special to 20, it just seemed to work at that point of time. So this is again a place where we need to see, because we do not have a precise indicator of how many failures to see. That would have come if this log 1 by gamma term were not there. That would have been easier, but that is not the case. So we had to just choose some number, we chose 20. Okay. So for the remaining systems, so now what do we have? We have eliminated the obviously non-best systems, and we have seen sufficiently many failures to be able to talk about how often they may or may not fail. And in addition to those, we have a bunch of systems where we are yet to see any failures. What do we do is these systems, we give 10 times more samples, and the other systems, where we have not seen sufficiently many failures, we just keep giving them as many samples as we had stopped here. Right? Okay. Now, at the end of this stage, like this, 3 steps will keep happening iteratively till only the rarest arms remain. So only the arms for which alpha I equals alpha 1 will survive the stage 1. Once that is done, then we get to stage 2 and we repeat the parallel. Again, I mean, this is just, I mean, a more streamlined process of executing the same drag and stop routine, but I mean, this just makes more intuitive sense as opposed to solving the lower bound problem every time and then going on. So you can notice that, you know, when I'm sampling like in hundreds, thousands, or 10,000s, we are already incorporating some form of batch sampling. That there is room for improvement here. And lastly, what happens is we are able to meet the lower bound on expected sample complexity. But again, like we were thinking that probably this lower bound should be tighter. It also turns up in our computation. So we are off from it by a factor of 10, 100, that kind of. Okay. Lastly, the generalization is earlier we were looking at polynomials in gamma, if you remember. So reciprocals of polynomials in gamma, one by p1 gamma to the power n, that kind of an expression. Instead, it suffices to have each fi continuous and having value 0 at 0. In addition, we also want these functions to not go to 0 faster than polynomial gains. That's enough. I mean, we don't need these FIs to strictly be polynomials. Just being lower bounded by some polynomial is sufficient. Like I said sometime during the middle of the presentation that we also considered that the systems have different simulation costs or computation costs. We have skipped that here for simplicity and to deliver the insights more clearly. Okay, any more questions?
I have one question. Sure. So it's completely not technical. So basically, from your result, you want to find one of the, like, out of several designs, you want to find out a design which is safe, right? So by design, how do you get some kind, like here you are selecting like the best arm, right? How do you connect a design with an arm? Like,
so a design, when we are saying a design, it's basically a system that either fails or does not fail. This gives us a probability distribution.
Okay.
When we are simulating this design, what are we doing? We are drawing samples from that particular probability distribution. So when we have this many probability distributions, it automatically becomes a bandit problem.
okay. So you look at the probability of some kind of accident happening to a system and
Yeah.
work with it.
Yeah. Okay.
Let's thank you. One second.